So with Ubuntu, we're constantly looking at technology, the way in which people are deploying it, to predict where the market is going. And we see people deploying application infrastructure in a scale-out way. Very many nodes, potentially thousands or tens of thousands of nodes, and ARM fits that model very well.
We see hyperscale on ARM and x86 Atom as a great complement to virtualized cloud environments. ARM has been a supported Ubuntu platform for a while now. We first introduced ARM support in the 9.04 release 4 years ago.
It's why we've invested very heavily in Ubuntu Server for ARM, and now we treat Ubuntu Server for ARM like we treat any other architecture, whether it's Intel or x64.
We've been working with the ARM community to make sure that hyperscale devices work, that they work properly in Ubuntu, but also just that ARM itself works properly. There's not just ARM issues, but there's also management controller issues that need to be working not only in Ubuntu, but just in general, so that you can do hyperscale things. You don't want to bring up 1,000 nodes and all have them trying to do DHCP at once, for instance.
We're very excited to bring landscapes management capabilities to the hyperscale world, both on ARM and Intel platforms. So today we have come to MIT to find some real-world application for hyperscale ARM computing. We're looking for interesting applications of ARM as applied to large-scale computing. And this place is right at the center of efforts aimed at making ARM a viable cluster computing platform. They have some very interesting bits of hardware here, and we will not go into any specifics, but let's just say that we have serial number 1 and they have serial number 0.
MIT's interest in low-power cluster designs is twofold. We have a general interest in performance per watt ratio to feed into our various research efforts in HPC as a computer science discipline. That is to say that any chance that we can get the same production code running at the performance levels we're accustomed to for less electricity is a win for us. What we built today is a 60-core TI Panda board cluster, which represents ARM v7 architecture. And the instantiation that we had from Texas Instruments is the OMAP4 processor, which is a dual ARM Cortex-A9, varying in frequency between 300 megahertz and 1.01 gigahertz. We used 4 different revisions of Ubuntu. We tried Oniric, Natty, Precise, and Quantum, just to demonstrate the ease of a heterogeneous landscape cluster. Software vendors like Canonical have started compiling ARM operating systems and applications to take advantage of hard float. This has effectively introduced a much faster, more efficient ARM architecture in code so that we can run our algorithms faster. We built a 30-node landscape cluster today. This 30 nodes represents 60 ARM Cortex-A9 cores. And more importantly, it represents an efficient and effective way to do out-of-band management via a single landscape interface. The advantages to that are we now no longer have to steal bandwidth, even small pieces of bandwidth, from our production network connection, which is, in this case, Ethernet. We talk to our Panda board clusters through an out-of-band network, USB net, on the mini USB-based OTG on-the-go network.
In an industry first, Landscape is adding ARM architecture support to our best-of-breed Ubuntu Enterprise Systems Management solution, ready for production use later this summer, and available today in beta for testing.